We continue our discussion on Einstein and special theory of relativity. Today, we will be discussing time dilation, length contraction and also Lorentz transformation. Now, first we consider the following experiment. I am inside a train and let us suppose you are on the platform. I am moving with a velocity of let us suppose 100 kilometers per hour. So, I am moving in this particular direction with a velocity 100 kilometers per hour. Now, I have a tennis ball or a cricket ball in my hand and I throw the cricket ball along the length of the train with a velocity let us suppose 20 kilometers per hour. So, the ball is moving away from me with a velocity 20 kilometers per hour and I am moving with respect to you with a velocity 100 kilometers per hour. Then what you will observe is that the cricket ball is moving away from you with a velocity of about 120 kilometers per hour. Now, I take a laser pointer. I switch it on and switch it off. I produce a light pulse. Now, I produce the light pulse along the direction of the movement of the train. Now, the light pulse is moving away from me with a velocity 3 into 10 to the power of 8 meters per second. Then what Einstein said in 1905 is that the light pulse will also move with the same velocity with respect to you who is standing on the platform. So, what he said was in his 1905 paper that light always propagates in free space with a definite velocity v that is independent of the state of motion of the emitting body. This quantity v these days we replace it by a symbol small c. So, that the velocity of light is independent of the state of motion of the emitting body. This was experimentally verified by Alvager and his colleagues in the year 1964, where they took a mu-meson moving with a velocity which is very close to that of light. Now, when it emitted, it disintegrates to 2 gamma ray photons with a mean lifetime, as I have shown here, with a very small mean lifetime of 8 into 10 to the power of minus 17 seconds. Now, the velocity of the gamma ray photon was measured and it was found that it was equal to 3 into 10 to the power of 8 meters per second. So, that the velocity of the light quantum released in the disintegration of the mu-meson is the same even if mu-meson was at rest. Why do we require a pi 0 meson? Because if you want to move a laser pointer with a velocity which is very close to that of light, it will require an enormous amount of energy. This I had explained in the very first lecture. So, therefore, it is very difficult for an object that we see in our daily lives to make it move with an extremely high velocity. So, the pi 0 meson moves with a very high velocity, and therefore, it proved the hypothesis, the postulate that was put forward by Einstein in 1905. Now, let us see the consequences of this. I now take a laser pointer and pointing upwards, and I switch it on and switch it off. I produce a light pulse. I am still inside the moving train. Now, there is let us suppose a mirror at the top of the roof. The light pulse gets reflected and comes back, and adjacent to this laser pointer I have a small detector. Now, the time that it takes for the laser pulse to come and to go to the mirror, get reflected and come back to it is equal to 2 times h. H is, let us suppose, the height of the mirror, and divided by c. So, this will be the time taken. So, this for me who is inside the train, we will see that the time taken for the laser pulse to reach the mirror and come back to the detector will be 2 h by c. Now, for you, when the train is moving, and so therefore, when the laser pulse reaches the mirror has laterally shifted by a certain distance, and by the time it comes back to the detector has moved through a distance, and so therefore, the ray path will be a triangular path, which will be slightly longer than this path, which is 2 times h. The velocity of the light as measured by u will be is the same, that is Einstein's postulate, and so therefore, in your frame of reference you will record slightly longer time between the two events. What are the two events? The two events are the production of the light pulse, and the second event is its subsequent detection by the detector. So, after this paper was written, Einstein wrote to his friend that time is not absolutely defined, and this is one of the most profound statements made by Einstein. So, let us look at it carefully. So, I have a mirror which is at the top of the train. I have a light pulse which goes and gets reflected by the mirror, and I have a detector, I have a small detector which comes here, and this distance I represent by small h. So, in the frame of reference of the moving train, which is my S prime frame, the time interval between the two events is equal to 2 h by c, where h is the height of the mirror. This is my laser pointer, this is my laser pointer, and this is my detector. Now, with respect to you on the platform, the mirror has moved through a distance. When it so the light ray traverses this path and this path. So, let us suppose this point is P, this point is M stands for mirror, and this part is D. So, the detector has moved through a distance, and let us suppose you on the platform measure a time difference between the two events as delta t, and the train is moving with a velocity u. So, this distance is equal to u times delta t. So, therefore, the time taken that you will observe between the two events, the production of the light pulse and its subsequent detection by d, will be equal to P m plus m d divided by c, but P m is equal to m d. So, this will be 2 times P m divided by c. C is the speed of light in free space. And so therefore, delta t whole square, so delta t whole square is equal to 4 by c square, 4 by c square p m square. Now, p m square will be, this is h. So, 4 by c whole square is equal to p m square will be h square plus u delta t by 2 whole square. So, I will have delta t whole square is equal to 4 h square by c square. So, delta t whole square is equal to 4 h square by c square, that is the time interval between the two events that I have measured inside the train, plus 4 and 4 cancels out. So, you get u square by c square delta t square. If I take in this side, so I get delta t becomes equal to 1 over under root of, this is 1 minus u square by c square, 1 minus u square by c square delta t prime. So, this factor is known as the Lorentz factor. This factor is known as a Lorentz factor and is denoted by the symbol gamma. So, we finally get the relation that delta t, as you observe on the platform, is equal to gamma into delta t prime, and gamma is known as the Lorentz factor, which is equal to 1 minus u square by c square, where u is the velocity of the train. For most velocities, u is very, very small, u by c is very, very small compared to 1. In such a case, gamma is approximately equal to 1, and then delta t is equal to delta t prime. However, gamma is always greater than or equal greater than 1, and so therefore, this time is slightly greater than this time. This delta t prime is known as the proper time, because the two events occur at the same space point, and delta t is known as the improper time, and time gets dilated. This is the phenomenon of time dilation. So, let me show this once again. I am inside the train, and there is a bulb which emits light. You have a pulse of light, and there is a mirror at a height h, and this is the detector. So, the time interval in the S prime frame is given by delta t prime is equal to 2 h by c, and then for the observer A on the platform, by the time the light reaches the detector, let us suppose the time interval between the two events is delta t as measured by A, then the distance between P and D as seen by A will be equal to u times delta t, and so therefore, the time interval that you will see will be P m plus m d divided by c, but P m is equal to m d is equal to, by using Pythagoras theorem, so much. So, therefore, you will have the same expression delta t whole square is equal to 4 h square by c square plus u delta t by c whole square. So, you finally get the result that delta t whole square is equal to delta t prime whole square plus u square by c square delta t whole square. You take it to this side and you get this relation, and therefore, delta t becomes 1 over under root of 1 minus u square by c square delta t prime. Delta t prime is the time interval as seen by S prime, where the two events, the production of the light pulse and its subsequent detection, occurs at the same space point. So, delta t prime is known as the proper time, and delta t is known as the improper time. So, you get finally the result that the time gets dilated as seen by the observer on the platform. This will be slightly more. So, the conclusion is that the time interval, because of the Einstein's postulate, the time interval between two events occurring at the same place in a particular reference frame S prime which is referred to as the proper time, is equal to 1 minus u square by c square under root times the time interval between the two events in any reference frame S moving with relative speed u. Let us suppose I have a particle or an object moving with a tremendously large velocity, almost 99.5% of the velocity of light. If that is the case, then 1 minus u square by c square will be 1 minus 0.995 whole square. So, this is, if you do this as very simple algebra, you will get 0.1. So, delta t prime is equal to 0.1 times delta t, and the Lorentz factor, which is the inverse of this factor, will be equal to 10. So, let us consider twins. A and B are twins. So, I am moving, their origins coincide at t equal to 0 and t prime equal to 0, and B is inside a spacecraft, and it quickly accelerates to a velocity 0.995 c and tries to go to a nearby star, which is, let us suppose, 5 light years away. So, what is 5 light years the distance? The distance 5 light years, that the light will take 5 years to traverse from this point to this star. So, in fact, the closest star is about 3.8 light years away. So, light takes about 3.8 years. So, we assume that, let us suppose, the nearest star, which is known as Proxima Centauri, is about 5 light years away. So, as far as, because this spacecraft is moving with a velocity which is very close to that of light, A will think that B will take 5 years to go from here to the nearby star. But for the observer B, the Lorentz factor is 10. So, B will think that it has taken only 0.5 years. So, therefore, his watch will show that it has taken 0.5 years. He then quickly turns around and comes back to Earth, and for him the time interval spent is 1 year and the time interval spent by A is 10 years. So, let us suppose both of them were 30-year-old when they started. After B returns, A will become 40 years old, whereas B will become 31-year-old. So, this is this has led to a lot of controversy, but there is no doubt that there is a time difference, and B and that A would have aged significantly after such a traversal. Now, the fastest aircraft X-15 flew with a speed of about 7230 kilometers per hour, which is equivalent to about 2 kilometers per second. This is about 0.0007% of the speed of light. During re-entry, the Apollo space shuttle attained a speed of about 28,000 kilometers per hour, which is really an extremely high speed, which is equivalent to about 8 kilometers per second. That is about 0.0026% of the speed of light. We assume a speed of about 30 kilometers per hour, which is 15 times that of the fastest aircraft, and this is an incredibly large velocity. However, for the observer on Earth, such a spacecraft will take about 18 million seconds, which is slightly less than 7 months to reach the planet Jupiter, which is about 540 million kilometers from the Earth, and for the person inside the spacecraft, the time taken will be about a tenth of a second less than that observed on Earth. So, that for most objects, for even the space, the fastest aircraft, the speed of these fastest aircraft is so small in comparison to the velocity of light, that the time difference between delta t and delta t prime is extremely small and very difficult to measure. But otherwise, but it is true that there will be a time dilation, and that the person who is going on this spacecraft, when he comes back, his watch will be slightly different from the person who stays back on the Earth. Thus, unless the velocities are close to that of the speed of light, the time difference between the events as observed by the two observers will be very, very small. Now, let me consider another phenomenon which is a consequence of that length contraction. Now, let us consider the following experiment. Now, I am inside the moving train and I have a pointer which comes out of the moving train from a window. Now, you are on the platform and you hold a rod. Let us suppose that rod length is L0 or 1 meter. Now, for you the rod is at rest, and so you measure what is known as the proper length of the rod. So, what is the proper length of the rod? If the rod is at rest with respect to you, then the length that you will measure is known as the proper length of the rod. So, let us suppose I want to make a measurement of the length of the rod and you also want to make a measurement of the length of the rod. So, I am with respect to you, I am moving like this. So, I consider two events. One event is that the end of the pointer that I have ejecting out of the window hits one end of the rod, and the other event is when it hits the other end of the rod. These 2 points are being hit at different space points with respect to you, because with respect to you I am moving like this. So, first it hits here, then it hits here, and you make a measurement of the time interval between these two events. I am moving with respect to you with a velocity u. So, the time interval between the two events is u times delta t. But what I will measure is that for me you are moving like this and the pointer is at the same space point. So, I will measure the proper time, because both the events are occurring at the same space point. So, I will measure the distance u delta t prime. So, therefore, since delta t prime is slightly less than delta t, so I will measure a slightly smaller length. So, length will get contracted, and by the same factor as the inverse of the Lorentz factor. So, let me show you once again. So, A is on the platform and B is inside the train, which is moving with respect to A with velocity u in the plus x direction. Now, A is holding a rod which is of length L0. I have a pointer coming out of the window at a fixed space point in my frame of reference. It is, let us suppose, at a distance of 1 meter from the origin O prime. So, this point remains fixed with respect to me. So, what A will see will be that the pointer will go from this point to this point. So, for her the two events, the pointer hitting the end r and the pointer hitting the r prime will occur at different space points. On the other hand, for the person B, for me the rod will move in this direction. So, the rod this pointer hitting the end of the rod r and the pointer hitting end r prime, let us suppose the time interval is delta t prime. So, the length that I will measure will be L is equal to u delta t prime, where delta t prime is the time interval, this is the proper time interval between the two events. On the other hand, she will measure L0 is equal to u delta t, because for her the events occur at r and at r prime. The pointer first hits the end r, then it hits the r prime, which are at different space point. So, she will measure the improper time. So, L0 will be equal to u delta t, but as I have just now shown little earlier, the delta t is slightly greater than delta t prime. So, therefore, the length that I will measure will be slightly less, and the factor will be the same as, because delta t prime by delta t is equal to 1 over under root of minus u square by c square. So, I will measure a contracted length which is given by L0 into under root of 1 minus u square by c square. Now, this is the very famous experiment of mu-mesons which validated the theory of relativity, the special theory, the time dilation that is predicted by the theory of relativity. Now, mu-mesons, and in fact this experiment was suggested by Homi Bhabha in around 1937. Now, in this experiment consisted of that the mu-mesons are created in the outer end of the atmosphere, and they have a half life of about 1.5 microseconds, 1.5 microseconds. So, the experiment was that at the top of a hill, and the hill is about, let us suppose, 2 kilometers height. So, let us suppose you have 100 mu-mesons crossing an unit area per second. I have 100 mu-mesons crossing an unit area per unit time. Now, there is an observer on the top of the mountain which is at a height of 2 kilometers, and there are 100 mu-mesons which are hitting an unit area per second. Now, if you do the calculation, because the mu-mesons are moving with a velocity equal to 0.995 c. So, they are moving with a velocity which is very close to that of light. So, the observer A, who is on the ground, he will think that if you make a simple calculation that how much time will it take for the mu-meson to travel a distance 2 kilometers with a velocity, if it is moving with a velocity 0.995 c, then you will find that it will take about 6.4 microsecond. So, therefore, according to A, the mu-mesons will take 6 microseconds, which is 4 half lives. That means the total number of mu-mesons will be 100, 100 was observed here, multiplied by half, multiplied by half, multiplied by half, multiplied by half, because there are 4 half lives. So, this will be 100 divided by 16 will be about. So, therefore, at the base we should observe only 6 or 7 mu-mesons to arrive. But when the experiment was carried out, it was found that the number of mu-mesons that arrived at the base was much higher, and that is because in the rest frame of the mu-meson, because it is moving with a velocity 0.995 c, the Lorentz factor is about 10, as I had shown you, and so therefore, in the rest frame, if the mu-meson is inside a satellite and I am inside that satellite, then in that frame of reference, it will move only 0.64 microsecond, 1/10 of that, and in that small amount of time there will be almost no mu-meson that would have decayed. So, therefore, the actual experiment was something like this, that as you know, as I told you, that the half life of the mu-meson, is about 1.525 microsecond. Now, as you know, they follow the law of radioactive decay. So, n is equal to n0 e to the power of minus t by tau. Tau is known as the mean lifetime. So, when this becomes half, so n is half of n0. So, then this will be e to the power of minus t half, this is the half life, divided by tau. So, if I take the natural logarithm, so log 2 is equal to t half divided by tau. So, t half is equal to log 2 times tau, and log 2 is about 0.693, log 2 to the base e. So, therefore, tau comes out to be about, if you multiply 1.525 to this thing, about divide by that 2.2 microsecond. So, therefore, the mean lifetime of the mu-meson is 2.2 microseconds. Now, what was observed at the top of the mountain? At the top of the mountain, the number of mu-mesons that was crossing a particular area in a typical observation was found to be 568. 568. So, according to the observer A, this takes about 6.4 microsecond for the mu-meson to traverse this distance. So, therefore, the number of particles that should reach the earth will be 568, n will be n0 568 e to the power of minus t by tau. So, this will be equal to 568 e to the power of minus 6.4 divided by 2.2 is the 2.2 microsecond is this. So, if you do the algebra, then this comes out to be about 31. That means, if there are 568 mu-mesons reaching at the top of the atmosphere, then on the ground there should be only 31 mu-mesons that should be observed. However, as I told you that because of the time dilation, what we should expect is that in the reference frame of the mu-meson, the time elapsed is only 0.64 microsecond. So, therefore, the number that you observed according to the special theory of relativity will be n0 e to the power of minus t by tau, and n0 is 568, and this is t is minus 0.64 microsecond divided by 2.2. If you do the algebra, then you will find that this number is 31, and this compares very well with experiment. So, let me go back to my slide that mu-meson has a half life of about 1.25 microsecond. It disintegrates to an electron and a neutrino and an antineutrino, and the half life is 1.525. So, here is the observer. Let us suppose there is an observer sitting on the ground. The experiment was carried out at the top of Mount Washington in the United States, and this was around 1938 or 39, that the height was about 2 kilometers, slightly less than 2 kilometers, 1920. So, the mu-meson was moving with a velocity, was found to move with a velocity of about 0.995 c, and if you the inverse of the Lorentz factor is about 0.1. So, for an observer on the earth, the mu-meson would take about 6 microsecond or 4 half lives to reach earth, but if for a person inside the spaceship, it will take only about 0.6 microsecond, less than half of the half life. And so, therefore, the number of mu-mesons that will arrive will be actually I'm sorry, this should not be 31, I am sorry, this should be 425, I am sorry. If you do this, this is 425. So, that the number of mu-mesons that will reach the earth is 425. I am sorry, I did the slightly wrong calculation. So, and it should be very large in number. So, this is what is indeed observed in the experiment. There is another way to look at this experiment. If I am inside a spaceship and the mu-meson is at rest, that means the spaceship is moving with a velocity 0.995 with respect to the observer on the ground, then I will see the earth moving towards me with a velocity 0.995 c. I am inside the spacecraft, and this will be a contracted distance. So, the earth will hit me, the contracted distance will be 1/10 of this distance. So, this will take for the earth to reach the spacecraft the 1/10 of that time. So, instead of 6.4 microsecond, it will be 0.64 microsecond. So, in that time only very few of the mu-mesons will disintegrate. Homi Bhabha, in a paper published in Nature in 1938, was the first to point out. As you all know, Homi Bhabha was the founder of our nuclear India, was the first to point out that the measured lifetime of a mu-meson in flight is affected by the time dilation predicted by Einstein's special theory of relativity. And we know today that this measurement is the most direct demonstration of that phenomena. This is what Lord Penny has written in Proceedings of the Royal Society. This is a photograph of Homi Bhabha with Einstein. Here is Yukawa, the famous nuclear physicist, and John Wheeler, and this photograph was taken at Princeton. Now, let me now discuss the phenomenon of Lorentz transformation. I have again two observers, A and B. B is inside a moving train which is moving with velocity u with respect to A, and the origins coincide at t equal to 0 and at t prime equal to 0. So, A is on the platform and B is inside a train which is moving with respect to A with velocity u in the plus x direction. When O coincides with O prime, the clocks are synchronized, so that t equal to 0 equal to t prime. Now, let us consider that, so at t equal to t prime equal to 0, the origins coincide. So, at this time x is equal to 0 and x prime is equal to 0. Now, in time t, the observer B has moved through a distance u delta t, ut, because the train is moving with respect to A with a velocity u. So, the observer inside the train, there is a point P which is at a distance of x prime with respect to the observer inside the train. This distance, this is the distance as measured by the observer B inside the train. So, as far as A is concerned, he will measure a contracted distance, that is, he will measure that if this coordinate of the point P as measured by A is given by x, then as x will measure that x is equal to ut plus this distance will be x prime under root of 1 minus u square by c square x prime. Please see, an event occurs at the point P which is at a distance x prime from the origin of the moving train. So, this distance is measured by B. A will measure a slightly contracted distance, and in that time, let us suppose the event occurs at time t with respect to A. So, then x will be equal to the x coordinate as measured by A will be equal to ut plus under root of 1 minus u square by c square into x prime. This quantity is the Lorentz factor. So, this will be plus 1 by gamma x prime. So, I will obtain from here, if I bring this to this ut to the left hand side. So, I get x minus ut times gamma is equal to x prime. So, x prime is equal to gamma times x minus ut. This is one of the equations describing what is known as the Lorentz transformation. Now, let me see what B will see. So, the event has occurred, the event for B, which is the B is here, and this is the event occurs at a point P. This is at a distance of x for A, and for B it is at a distance x prime, and the event occurs at the point P at time t prime for the observer B. So, in this time, the distance that A has moved in the opposite direction will be this distance will be u times t prime. This distance x between the origin and the point P is measured by A. So, B will measure a contracted distance. So, what she will say is that x, the contracted distance that B will measure will be x by gamma. So, x by gamma is equal to x prime plus u t prime. So, this will be x is equal to gamma of x prime plus u t prime. So, I have derived the two equations. So, we arrive at two equations which are given by gamma into x minus u t, and the second equation is x is equal to gamma into x prime plus u t prime. These two equations are known as the equations deriving Lorentz transformation. So, what I do is I substitute for x in this equation. So, I get x prime, let us do this little carefully, gamma x minus u t, and x is equal to gamma of x prime plus u t prime. This was x prime x and minus u t. So, let me simplify. So, this will be gamma square x prime plus gamma square u t prime, gamma square u t prime minus gamma u t. So, you will have, you take gamma u t on this side. So, you get gamma u t on this side. So, this will be gamma square minus 1 times x prime plus gamma square into u into t prime. So, this quantity gamma square minus 1 will be equal to 1 minus u square by c square, 1 minus u square by c square minus 1. So, this will be 1 minus 1 u square by c square divided by 1 minus u square by c square. So, this is equal to gamma square u square by c square. So, therefore, you will have gamma u t is equal to gamma square minus 1. So, that is gamma square u square by c square x prime plus gamma square u t prime. So, u, if you cancel u, 1 u and 1 u cancel, and then you take gamma square outside. So, you get gamma square will be equal to this will be within brackets u by c square x prime plus t prime. So, 1 gamma cancels out with this. So, therefore, t will be equal to gamma times u by c square x prime plus t prime. So, this is an equation which we have derived from the Lorentz transformation. So, I may write down delta t, the time interval between two events in the S frame, will be equal to gamma into u by c square multiplied by delta x prime plus delta t prime. So, let me consider two specific cases. First, case 1, in which the two events occur at the same space point in S prime reference. So, therefore, the two events occur at the same value of x prime. So, delta x prime is equal to 0. So, then you will have delta t is equal to gamma delta t prime. So, this is my time dilation that we had derived earlier. This is the, so the time dilation is contained in my Lorentz transformation. And let me take case 2, that two events occur at different space point in the S prime frame, but at the same instant. So, therefore, let us suppose delta t prime is 0. So, then you will have delta t which is equal to gamma u by c square into delta x prime. So, therefore, you get the case that if two events occur at two different space points, but simultaneously, then these two events are not simultaneous for the S frame. Let me show you these things again. So, these are the two equations describing what are known as Lorentz transformation and which we have derived using the phenomenon of length contraction. So, if we substitute x prime from equation 1 in equation 2, I will get this expression. If we substitute for x from equation 2, these are the two equations that you can derive from 1 and 2. So, 3 and 4 can be derived from 1 and 2. These are very simple algebraic equations. So, let me consider this equation t is equal to gamma t prime plus u x prime by c square, which I derived a few minutes earlier. Then time interval between the two events as seen by the observer in the S prime delta t is equal to gamma of delta t prime, which is the time interval between two events as seen in the reference frame S prime, multiplied by the u delta x prime by c square. If the two events take place at the same place in the S prime frame, then delta x prime is 0 and we obtain then delta t prime is the proper time, and delta t will be slightly greater than delta t prime. So, this is the phenomenon of time dilation. On the other hand, let us suppose I have an atom which emits out two photons and the two detectors are placed at the same distance from this atom. Then the time taken by the photon to reach here or to reach here will be the same. So, the two events, this detection by the two detectors are simultaneous as far as B is concerned, but they are at two different space points. So, delta t prime is 0, but delta x prime is 2L0. So, these two events will not be simultaneous with respect to the observer A. So, for the observer B on the moving train, the atom is at rest and emits two photons simultaneously in opposite directions. The two detectors D1 and D2 and are equidistant from the atom and detect the photons simultaneously. However, the two events are not simultaneous for the observer A. So, this is also a consequence of Lorentz transformation. Using these two equations and the fact that y is equal to y prime and z is equal to z prime, one can write down that x square minus c square t square. I square this and I square this and multiply it by c square. And if I write this down and carry out a very simple algebra, so you get x square minus c square t square is equal to x prime square minus c prime c square t prime square. So, you use now the equation because there is no motion in the y and z direction, that y is equal to y prime and z is equal to z prime. So, you get x square plus y square plus z square is equal minus c square t square is equal to x prime square plus y prime square plus z prime square minus c square t prime. Thus, it must be a spreading sphere in both the frames. In fact, the coordinate transformation in which this condition is satisfied is called the Lorentz transformation. So, let me mention that if I have a disturbance which emanates from the point O, then the equation of the sphere is that r the wave will move through a distance t, through a distance c t in time t. So, the radius of the sphere will be r is equal to c t. So, r square is equal to c square t square. So, x square plus y square plus z square minus c square t square is equal to 0. So, this represents, this condition represents the fact that you have a spherical wave front here. So, what this equation tells us is that it must be a spreading sphere in both S frame and as well as in the S prime frame. In fact, the coordinate transformation in which this condition is satisfied is called the Lorentz transformation. Now, you have for this the energy and the energy and momentum, you have the energy related to momentum as E square is equal to P square C square plus m naught square C4. Now, for the photon, the rest mass of photon is 0. So, you have E square by C square is equal to P square, and P square is equal to P x square plus P y square plus P z square. So, therefore, you will have for the photon P x square plus P y square plus P z square is equal to E square by C square, and in the S prime frame P x prime square plus P y prime square plus P z prime square is equal to E prime square by C square. Thus, P x square plus P y square plus P z square minus E square by C square is equal to P x prime square plus P y prime square plus P z prime square minus E prime square by C square. So, if you compare this with your x relation, thus in the transformation laws we must replace x by p x, y by p y, z by p z and t by e square by e by c square. Thus, because the two relations are identical, we may replace in determining the laws of transformation between p x and p x prime, we may replace x by p x, y by p y, z by p z and t by e by c square. So, if I do that, these are the Lorentz transformations that I had derived. So, I replace x prime by p x prime, x by p x and t by e by c square. Similarly, I replace t prime by e prime by c square and do a little bit of algebra. So, I get these are the equations which transform energy and momentum. Now, let me write down the first equation, that p x prime is equal to gamma times p x minus u e by c square. And then you of course have p y prime is equal to p y and p z prime is equal to p z. So, in the S prime frame, let us suppose there is an atom which is moving in the x direction with velocity u, and it emits a photon in the direction of theta prime. So, this is my S prime, this is x prime axis and this is the y prime axis. And in the S frame, the same photon appears in the direction say theta, and the frequency is h nu, the momentum is h nu by c, here the momentum is h nu prime by c. So, this is my x axis and this is my y axis. So, because p y prime is equal to p y, so you will have h nu prime by c sin theta prime, this is the y component of the momentum, is equal to h nu by c sin theta. So, you will have nu prime sin theta prime is equal to nu sin theta. Let me now consider the other equation. The other equation is p x prime is equal to, let me write it down again, gamma of p x minus u e by c square. So, p x prime is equal to the momentum, the x component of the momentum, that is h nu prime by c into cos theta prime. This is equal to gamma into p x, that is h nu by c cos theta minus u h nu, that is cos theta e is h nu by c square. Now, let me assume, let me go back to the previous slide, And let us suppose the emission is such that theta prime is equal to 0. If theta prime is equal to 0, then from this equation we get theta is because the left hand side is 0. So, therefore, if theta prime is 0, then theta is also 0. So, if I now substitute theta prime equal to 0 and theta equal to 0, this is 1 and this is 1. So, h by c if I cancel out, so you get nu prime is equal to gamma. The nu also I take outside, so I will get 1 minus u by c, 1 minus u by c. So, therefore, you will get gamma is equal to, as you know, this is equal to 1 minus u square by c square, that is the Lorentz factor. This is nu multiplied by 1 minus u by c. So, you finally get the relation that this is equal to nu times under root of 1 minus u by c divided by 1 plus u by c. Since this is the redshifted frequency that I had used right in the beginning, right in lecture 1 for a photon for which the source is moving away from the observer. So, these are the Doppler shifted frequencies that we have derived. In an exactly similar manner, if I have theta prime is equal to pi, then theta is also equal to pi, and then we can find out that the Doppler shifted frequencies are blue shifted. The source is moving towards the observer. Let us try to summarize what we have done today. From the postulates of the special theory of relativity, which was put forward by Einstein in 1905, we derived the concept of time dilation. We first defined the proper time, which was the time interval between two events which occur at the same space point. Similarly, we obtained the relation describing length contraction. The proper length of a rod is that length in which the rod is at rest. In any other frame in which the rod is moving, appears to move, it will measure a contracted length. Using these two concepts, we discussed the mu-meson experiment, which established beyond doubt the time dilation as predicted by the special theory of relativity. And the mu-meson experiment was first suggested, as I had mentioned, by Homi Bhabha in 1938. Then, using the length contraction, we derived the Lorentz equations describing the Lorentz transformation, and from those equations once again we derived the fact that there is time dilation, and also that two events which are simultaneous in a particular reference frame will not be simultaneous in another reference frame at two different space points. Then we derived the transformation for the momenta of the photon, and using that we could derive the expressions for the frequency shift, for the Doppler shift of the radiation that is emitted by the atom. These Doppler shifted expressions we had used right in the first lecture for the derivation of the E equal to mc square. So, that brings us to the close of this short 3 lectures on special theory of relativity. My lectures have been based on a book that I have recently published on Einstein and special theory of relativity, which has been published by Viva Books. There are many other very nice books which have been written on theory of relativity, special theory of relativity. One is by Ralph Berlin, from Newton to Einstein, The Trail of Light. It is a very nicely written book published by Cambridge University Press. And then there is a classic text by Barry Casper and R. J. Noer, Revolutions in Physics, published by W. W. Norton and Company. Then of course, there is the famous Feynman lectures written by Feynman, Leighton and Sands, the famous Feynman lectures on physics, and the papers, the original papers of Einstein with a beautiful commentary, original 1905 papers of Einstein, which is known as the miracle year of Einstein. So, John Stashell's book, which is an inexpensive edition, is available in India. The title of the book is Einstein's Miraculous Year, 5 papers that changed the face of physics, and that is of course a classic in this. And of course, there are many other books which discusses the special theory of relativity. Regarding the biography of Albert Einstein, there is a very famous book edited by Schilp and Albert Einstein, philosopher scientist. Then there is a book by Albrecht Folsing on Albert Einstein, and then there is a very nicely written book on Einstein, his life and universe by Isaacson, and also a book by Andrew Robinson, which is an edited book. So, there are many other books which have been written not only on special theory of relativity, but also on the life and story of Albert Einstein. With this, I come to the end of these set of lectures. Thank you very much.